A $100 bill leans against an alarm clock. Figure 7 one time has an impact on the value of money. Credit, Modification of Time is Money by Marco Verch/Flickr, CC by 2. 0. Chapter Outline, 7.1 Now versus Later Concepts, 7.2 Time Value of Money, TVM Basics, 7.3 Methods for Solving Time, Value of Money Problems, 7. 4 Applications of TVM in Finance. One of the single most important concepts in the study of finance is the time value of money, TVM. This concept puts forward the idea that a dollar received today is worth more than, and therefore preferable to, a dollar received at some point in the future. The 3 primary reasons for this are that 1. Money received now can be saved or invested now and earn interest or a return, resulting in more money in the future. 2. Any promise of future payments of cash will always carry the risk of default. And 3. It is simple human nature for people to prefer making their purchases of goods and services in the present rather than waiting to make them at some future time. For this reason, it is important to incentivize people to give up their present consumption patterns by offering them greater value in the future. Based on the concept of TVM, it can be said that a dollar was worth more to us, and thus carried more value, yesterday than it is to us today. It also then follows that a dollar in our possession right now carries a greater value for us than a dollar we might receive tomorrow or at some other point in the future. The entire concept of the time value of money is particularly important because it allows savers and investors to make better informed decisions about what to do with their money. TVM can help a person understand which option may be best based on the critical factors of overall risk, rates of interest, inflation, and return. TVM can also be used to help a person understand how much money they'll need to save in an interest-bearing account in order to reach a desired financial goal, such as saving $50,000 in 10 years in an account that earns 4% compound interest each year. TVM is the key underlying principle of such important financial analytical activities as retirement planning, corporate capital project evaluation, and even deciding on your own personal investments and bank accounts. If the main concept behind the TVM is that a specific amount of money in hand now is worth more today than that same amount of money will be worth tomorrow, you might think that a person would be better off spending their money now rather than saving it for later use. However, we know that this is not always the case. Sometimes it is simply a better idea to save your money. While inflation can have the effect of making a dollar worth less tomorrow than it is worth today, the positive effect of compound interest works in favor of savers and investors. Learning outcomes. By the end of this section, you will be able to explain why time has an impact on the value of money, explain the concepts of future value and present value, explain why lump sum cash flow is the basis for all other cash flows, how and why the passage of time affects the value of money. The concept of the time value of money, TVM, is predicated on the fact that it is possible to earn interest income on cash that you decide to deposit in an investment or interest-bearing account. As time goes by, interest is earned on amounts you have invested, present value, which effectively means that time will add value, future value, to your savings. The longer the period of time you have your money invested, the more interest income will accrue. Also, the higher the rate of interest your account or investment is earning, again, the more your money will grow. Understanding how to calculate values of money in the present and at different points in the future is a key component of understanding the material presented in this chapter, and of making important personal financial decisions in your future. See Figure 7. 2. A graphical representation of 4 stacks of coins showing money in a deposit account earning interest in years 1, 2, 3, and 4. Year 1's coin stack is the smallest. The stacks get bigger in year 2, year 3, and year 4. Figure 7.2, the time value of money it is better to be paid today, or you will lose out on the money you would have earned in interest. The lump sum payment or receipt. The most basic type of financial transaction involves a simple, one-time amount of cash, which can be either a receipt, inflow, or a payment, outflow. Such a one-time transaction is typically referred to as a lump sum. A lump sum consists of a one-off cash flow that occurs at any single point in time, present, or future. Because it is always possible to dissect more complex transactions into smaller parts, the lump sum cash flow is the basis on which all other types of cash flow are treated. According to the general principle of adding value, every type of cash flow stream can be divided into a series of lump sums. For this reason, it is critical to understand the math associated with lump sums if you wish to have a greater appreciation and a complete understanding of more complicated forms of cash flow that may be associated with an investment or a capital purchase by a company. Learning outcomes. By the end of this section, you will be able to define future value and provide examples. Explain how future dollar amounts are calculated using a single period scenario. Describe the impact of compounding. Because we can invest our money in interest-bearing accounts and investments, its value can grow over time as interest income accrues or returns are realized on our investments. This concept is referred to as future value, FV. In short, future value refers to how a specific amount of money today can have greater value tomorrow. Single period scenario. Let us start with the following example. Your friend is considering putting money in a bank account that will pay 4% interest per year, and is particularly interested in knowing how much money they will have 1 year from now if they deposit $1,000 in this account. Your friend understands that you are studying finance and turns to you for help. By using the TVM principle of future value, FV, you can tell your friend that the answer is $1,040. The additional $40 that will be in the account after 1 year will be due to interest earned over that time. You can calculate this amount relatively easily by taking the original deposit, also referred to as the principal, of $1,000 and multiplying it by the annual interest rate of 4% for one period. In this case, 1 year. Interest earned equals 1,000 times 0. 4 equals 40. 7. By taking the interest earned amount of $40 and adding it to the original principal of $1,000, you will arrive at a total value of $1,040 in the bank account at the end of the year. So, the $1,041 year from today is equal to $1,000 today when working with a 4% earning rate. Therefore, based on the concept of TVM, we can say that $1,040 represents the future value of $1,001 year from today and at a 4% rate of interest. We will discuss interest rates and their importance in TVM decisions in more detail later in this chapter. For now, we can consider interest rate as a percentage of the principal amount that is earned by the original lender of funds and/or charged to the borrower of these same funds. Following are a few more examples of the single period scenario. If a person deposits $300 in an account that pays 5% per year, at the end of 1 year, they will have FV equals 300 plus 300 times 0. 5 equals 315. 7. If a company has earnings of $2, $50 per share and experiences a 10% increase in the following year, the earnings per share in year 2 are 2. 50 plus 2, 50 times 0, 10 equals $2, 75 per share. 7. If a retail store decides on a 3% price increase for the following year on an item that is currently selling for $50, the new price in the following year will be 50 plus 50 times 0, 3 equals 51, $50. 7. The impact of compounding. What would happen if your friend were willing to wait 1 more year to receive their lump sum payment? What would the future dollar value in their account be after a 2-year period? Returning to our earlier example, assume that during the 2nd year, your friend leaves the principal, $1,000, and the earned interest, $40 in the account, thereby reinvesting the entire account balance for another year. The quoted interest rate of 4% reflects the interest the account would earn each year, not over the entire 2-year savings period. So, during the 2nd year of savings, the $1,000 deposit and the $40 interest earned during the 1st year would both earn 4%. 1,000 times 0, 4 plus 40 times 0, 0.4 equals $41. 60. 7. The additional $1. $60 is interest on the 1st year's interest and reflects the compounding of interest. Compound interest is the term we use to refer to interest income earned in subsequent periods that is based on interest income earned in prior periods. To put it simply, compound interest refers to interest that is earned on interest. Here, it refers to the $1, $60 of interest earned in the second year on the $40 of interest earned in the first year. Therefore, at the end of 2 years, the account would have a total value of $1,081.60. This consists of the original principal of $1,000 plus the $40, $0 interest income earned in year 1 and the $41, $60 interest income earned in year 2. The amount of money your friend would have in the account at the end of 2 years, $1,081. $60 is referred to as the future value of the original $1,000 amount deposited today in an account that will earn 4% interest every year. Simple interest applies to year 1 while compound interest or interest on interest applies to year 2. This is calculated using the following method. Year 1, 1,000 times 0, 4 equals 40. Year 2, 1,040 times 0, 4 equals 41, 60. 6. So, the total amount that would be in the account after 2 years, at 4% annual interest, would be 1,000 plus 40, plus 41. $60 equals 1,081. 60. To determine any future value of money in an interest-bearing account, we multiply the principal amount by 1 plus the interest rate for each year the money remains in the account. From this, we can develop the future value formula. Future value equals original deposit times 1 plus R times 1 plus R. 7. In this formula, the number of times we multiply by 1 plus R depends entirely on the number of years the money will remain in the bank account, earning interest, before it is withdrawn in a final lump sum distribution paid out from the account at the end of the chosen savings period. The 1 in the formula represents the principal amount, or the original $1,000 deposit, which will be included in the final total lump sum payment when the account is closed and all money is withdrawn at the end of the predetermined savings period. We can write the above equation in a more condensed mathematical form using time value of money notation, as follows. FV equals future value. PV equals present value. Letter 1D45F equals interest rate. Letter 1D45B equals number off periods. 7. 8. Using these inputs, we have the following formula. FV equals PV times 1 plus letter 1D45F, letter 1D45B. 7. 9. With this equation, we can calculate the value of the savings account after any number of years. For example, suppose we are considering 3, 10, and 50 years from the original deposit date at the annual 4% interest rate. 3 years. FV equals 1,000 times 1. 4, 3 equals 1,000 times 1, 12,486 equals 124. 86. 10 years, FV equals 1,000 times 1. 1,000 times 148,024 equals 1,480. 24. 50 years, FV equals 1,000 times 1. 4, 50 equals 1,000 times 7, 106,683 equals 7, 106. $68. 7. 10. How can this savings account have grown to be so large after 50 years? This question is answered by the impact of compounding interest. Every year, the interest earned in previous years will also earn interest along with the initial deposit. This will have the effect of accelerating the growth of the total dollar value of the account. This is the important effect of the compounding of interest. Money grows in larger and larger increments the longer you leave it in an interest-bearing account. In effect, the compounding of interest over time accelerates the growth of money. In order to determine the FV of any amount of money, it will always be necessary to know the following pieces of information. 1. The principal, initial deposit, or present value PV. 2. The rate of interest, usually expressed on an annual basis as R. And 3. The number of time periods that the money will remain in the account N. The interest rate is often referred to as the growth rate, or the annual percentage increase on savings or on an investment. When the rate is raised to the power of the number of periods, the formula, 1 plus letter 1D45F, letter 1D45B, will yield a number that is commonly referred to as the future value interest factor, FVIF. As a result of this process, as n, time, or the number of periods increases, the future value interest factor will increase. Also, as our interest rate increases, the FVIF will increases. For these reasons, the future value calculation is directly determined by both the interest rate being used and the total amount of time, specifically, the number of periods being considered. Think it through. Calculating future values. Here's another example of calculating future values in multiple period scenarios. On a recent drive, you spotted your dream home, which is currently listed at $400,000. Unfortunately, you are not in a position to buy it right away and will have to wait at least another 6 years before you can afford it. If house values are appreciating at an annual rate of inflation of 4%, how much will a similar house cost after 6 years? Solution: in this case, PV is the current cost of the house, or $400,000. N is 6 years. R is the average annual inflation rate, or 4%, and we have to solve for FV. FV equals 400, 000 times 1, 046, equals 400, 000 times 1. 265,319 equals $506, 127. 61. 711. Therefore, under these circumstances, the house will cost $506,127. $60 after 6 years. How time impacts compounding. We have just seen that time will lead to the growth of our money. As long as the prevailing growth or interest rate of any account we have our money in is positive, the passage of time will have the effect of growing the value of our money. The longer the period of time, the greater the growth, and the larger the future value of the money will be. This can be reinforced very clearly with the following example. Melvin is saving money in an account at a local bank that earns 5% per year. He begins with a deposit in his account of $100 and decides to save his money for exactly 1 year. He will not be making any further deposits into the account during the year. Melvin will earn 5% times 100, or $5 in interest income. Adding this to the original deposit balance of $100 will give him a total of 100 plus 5, or $105, in the account at the end of 1 year. Melvin likes this idea and believes he may be able to keep his money in the account for a longer period of time. How much money will he have in his account without any further deposits at the end of years 2, 3, 4, and 5? Using the future value formula, the calculation is as follows. FV equals PV times 1 plus letter 1D45F, letter 1D45B. Year 2, FV equals 100 times 1 plus 0. 052 equals $110, 25. Year 3, FV equals 100 times 1 plus 0. 053 equals $115, 76. Year 4, FV equals 100 times 1 plus 0. 054 equals $121, 55. Year 5, FV equals 100 times 1 plus 0. 055 equals $127, 63. 712. How the interest rate impacts compounding. Melvin likes the idea of earning more money over time, but he also believes that what he would earn in interest may not be enough for some of the things he plans to buy in the future. His friend suggests finding an account or some form of investment with a greater interest rate than the 5% he can get at his local bank. Melvin thinks he can leave his money in an account or investment for a total of 5 years. He found investments that will provide annual returns of 6%, 7%, 10%, and 12%. Using the FV equals PV times 1 plus letter 1D45F, letter 1D45B formula, we can complete the following calculations for him. 5%, FV equals 100 times 1 plus 0. 055 equals $127, 63. 6%, FV equals 100 times 1 plus 0. 065 equals $133, 82. 7%, FV equals 100 times 1 plus 0. 075 equals $140, 26. 10%, FV equals 100 times 1 plus 0. 10, 5 equals $161, 5. 12%. FV equals 100 times 1 plus 0. 12. 5 equals $176. 23. 7. 13. Again, Melvin likes this information, and he states that he will try to find the highest interest rate available. This makes sense, but it's important to remember that investments are usually not guaranteed to earn you specific interest rates or rates of return. Most investments, other than treasury investments such as treasury bonds, carry some form of financial risk, either small or large, and the greater the rate of return, the more likely it is that the risk associated with the investment will also be greater. This risk does not have any effect on the future calculations we have just completed, but it is an important factor to bear in mind and consider well before moving ahead and putting your money in any investment or financial instrument. Learning outcomes by the end of this section, you will be able to explain how future dollar amounts are calculated, explain how present dollar amounts are calculated, describe how discount rates are calculated, describe how growth rates are calculated, illustrate how periods of time for specified growth are calculated, use a financial calculator and Excel to solve TVM problems. We can determine future value by using any of four methods. 1. Mathematical equations. 2. Calculators with financial functions. 3. Spreadsheets. And 4. FVIF tables. With the advent and wide acceptance and use of financial calculators and spreadsheet software, FVIF and other such time value of money tables and factors have become obsolete, and we will not discuss them in this text. Nevertheless, they are often still published in other finance textbooks and are also available on the internet to use if you so choose. Using timelines to organize TVM information, a useful tool for conceptualizing present value and future value problems, is a timeline. A timeline is a visual, linear representation of periods and cash flows over a set amount of time. Each timeline shows today at the left and a desired ending or future point, maturity date, at the right. Now, let us take an example of a future value problem that has a time frame of 5 years. Before we begin to solve for any answers, it would be a good approach to lay out a timeline like that shown in Table 7.1. Year 0, today, 1, 2, 3, 4, 5, Table 7. 1. The timeline provides a visual reference for us and puts the problem into perspective. Now, let's say that we are interested in knowing what today's balance of $100 in our saving account, earning 5% annually, will be worth at the end of each of the next 5 years. Using the future value formula, FV equals PV times 1 plus letter 1D45F letter 1D45B 714 that we covered earlier, we would arrive at the following values. $105 at the end of year 1, $110. $25 at the end of year 2, $115. $76 at the end of year 3, $121. $55 at the end of year 4 and $127. $63 at the end of year 5. With the numerical information, the timeline, at a 5% interest or growth rate, would look like Table 7.2. Year 0, 1, 2, 3, 4, 5, $100. $105. $110. $25, $115. $76, $121. $55, $127. $63. Table 7.2, using timelines to lay out TVM problems, becomes more and more valuable as problems become more complex. You should get into the habit of using a timeline to set up these problems prior to using the equation, a calculator, or a spreadsheet to help minimize input errors. Now we will move on to the different methods available that will help you solve specific TVM problems. These are the financial calculator and the Excel spreadsheet. Using a financial calculator to solve TVM problems, an extremely popular method of solving TVM problems is through the use of a financial calculator. Financial calculators, such as the Texas Instruments BAII plus TM Professional, will typically have 5 keys that represent the critical variables used in most common TVM problems: N, IY, PV, FV, and PMT. These represent the following: N, number of periods IY, interest rate, interest per year, PV, present value OFA lump sum V, future value OFA lump sum PMT. Payment 715, These are the only keys on a financial calculator that are necessary to solve TVM problems involving a single payment or lump sum. Example 1. Future value of a single payment or lump sum. Let's start with a simple example that will provide you with most of the skills needed to perform TVM functions involving a single lump sum payment with a financial calculator. Suppose that you have $1,000 and that you deposit this in a savings account earning 3% annually for a period of 4 years. You will naturally be interested in knowing how much money you will have in your account at the end of this 4-year time period, assuming you make no other deposits and withdraw no cash. To answer this question, you will need to work with factors of $1,000, the present value, PV, 4 periods or years represented by N, and the 3% interest rate, or IY. Make sure that the calculator register information is cleared, or you may end up with numbers from previous uses that will interfere with the solution. The register clearing process will depend on what type of calculator you are using, but for the TBA-II plus TM professional calculator, clearing can be accomplished by pressing the keys 2ND and FV-CLR-TVM. Once you have cleared any old data, you can enter the values in the appropriate key areas, 4 for N, 3 for IY, and 1,000 for PV. Now you have entered enough information to calculate the future value. Continue by pressing the CPT, compute key, followed by the FV key. The answer you end up with should be displayed as 1,125.51, see Table 7.3. Step description: enter display 1 clear calculator register CEC0. 2. Enter present value. As a negative integer, 1,000 plus PV equals minus 1,000. 3. Enter interest rate 3 IY equals 3 4. Enter time periods 4 NN equals 4 5. Indicate no payments or deposits PMT equals 0. 06. Compute future value CPT FV equals 1,125.51. Table 7. 3 calculator steps for finding the future value of a single payment or lump sum. 1 important notes for using a calculator and the cash flow sign convention. Please note that the PV was entered as negative $1,000 or $1,000. This is because most financial calculators and spreadsheets follow something called the cash flow sign convention, which is a way for calculators and spreadsheets to keep the relative direction of the cash flow straight. Positive numbers are used to represent cash inflows, and negative numbers should always be used for cash outflows. In this example, the $1,000 is an investment that requires a cash outflow. For this reason, minus 1,000 is entered as the present value, as you will be essentially handing this $1,000 to a bank or to someone else to initiate the transaction. Conversely, the future value represents a cash inflow in 4 years' time. This is why the calculator generates a positive 1,125.51 as the end result of this calculation. Had you entered the present value of $1,000 as a positive number, there would have been no real concern, but the ending future value answer would have been returned expressed as a negative number. This would be correct had you borrowed $1,000 today, cash inflow, and agreed to repay $1,125.51, cash outflow, 4 years from now. Also, it is important that you do not change the sign of any input value by using the minus key. For example, on the TBA-II plus TM professional, you must use the plus key instead of the minus key. If you enter 1,000 and then hit the plus key, you will get a negative 1,000 amount showing in the calculator display. An important feature of most financial calculators is that it is possible to change any of the variables in a problem without needing to re-enter all of the other data. For example, suppose that we wanted to find out the future value in our bank account if we left the money from our previous example invested for 20 years instead of 4. Before clearing any of the data, simply enter 20 for N and then press the CPT key and then the FV key. After this is done, all other inputs will remain the same, and you will arrive at an answer of $1,806. 11. Think it through how to determine future value when other variables are known. Here's an example of using a financial calculator to solve a common time value of money problem. You have $2,000 invested in a money market account that is expected to earn 4% annually. What will be the total value in the account after 5 years? Solution: follow the recommended financial calculator steps in Table 7.4. Step description: enter display 1 clear calculator register CEC0. 2 enter present value as a negative integer 2000 plus PV equals minus 2000. 3 enter interest rate 4 IY equals 4. 4 enter time periods 5 NN equals 5 indicate no payments or deposits PMT equals 0. 6 compute future value CPT FV equals 2433. 31 Table 7.4 Calculator steps for determining future value. The result of this future value calculation of the invested money is $2,433. 31. Example 2. Present value of lump sum. Solving for the present value, discounted value, of a lump sum is the exact opposite of solving for a future value. Once again, if we enter a negative value for the FV, then the calculated PV will be a positive amount. Taking the reverse of what we did in our example of future value above, we can enter minus 1,125. 51 for FV, 3 for IY, and 4 for N. Hit the CPT and PV keys in succession, and you should arrive at a displayed answer of 1,000. An important constant within the time value of money framework is that the present value will always be less than the future value unless the interest rate is negative. It is important to keep this in mind because it can help you spot incorrect answers that may arise from errors with your input. Think it through. How to determine present value when other variables are known here is another example of using a financial calculator to solve a common time value of money problem. You have just won a second prize lottery jackpot that will pay a single total lump sum of $50,005 years from now. How much value would this have in today's dollars, assuming a 5% interest rate? Solution: follow the recommended financial calculator steps in Table 7.5. Step description: enter display 1 clear calculator register CEC0. 2 enter future value as a negative integer 50,000 plus FV equals minus 50,000. 3 enter interest rate 5 IY equals 5. 4 enter time periods 5 NN equals 5 indicate no payments or deposits PMT equals 0. 6 compute present value CPT PV equals 39,176. 31 Table 7.5 Calculator steps for determining present value. The present value of the lottery jackpot is $39,176. 31. Example 3. Calculating the number of periods. There will be times when you will know both the value of the money you have now and how much money you will need to have at some unknown point in the future. If you also know the interest rate your money will be earning for the foreseeable future, then you can solve for N, or the exact amount of time periods that it will take for the present value of your money to grow into the future value that you will require for your eventual use. Now, suppose that you have $100 today and you would like to know how long it will take for you to be able to purchase a product that costs $133. $82. After making sure your calculator is clear, you will enter 5 for IY, minus 100 for PV, and 133. 82 for FV. Now press CPT-N, and you will see that it will take 97 years for your money to grow to the desired amount of $133. $82. Again, an important thing to note when using a financial calculator to solve TVM problems is that you must enter your numbers according to the cash flow sign convention discussed above. If you do not make either the PV or the FV a negative number, with the other being a positive number, then you will end up getting an error message on the screen instead of the answer to the problem. The reason for this is that if both numbers you enter for the PV and FV are positive, the calculator will operate under the assumption that you are receiving a financial benefit without making any cash outlay as an initial investment. If you get such an error message in your calculations, you can simply press the CEC key. This will clear the error, and you can re-enter your data correctly by changing the sign of either PV or FV but not both of these, of course. Think it through. Determining periods of time here is an additional example of using a financial calculator to solve a common time value of money problem. You want to be able to contribute $25,000 to your child's first year of college tuition and related expenses. You currently have $15,000 in a tuition savings account that is earning 6% interest every year. How long will it take for this account grow into the targeted amount of $25,000, assuming no additional deposits or withdrawals will be made? Solution: Table 7.6 shows the steps you will take. Step description: enter display 1 clear calculator register CEC002 enter present value as a negative integer 15,000 plus PV equals minus 15,000. 03 enter interest rate 6 IY equals 604 enter future value 25,000 FV equals 25,000. 05 indicate no payments or deposits PMT equals 006 compute time periods CPT NN equals 8. 7667 Table 7.6 Calculator steps for determining period of time. The result of this calculation is a time period of 876.67 years for the account to reach the targeted amount. Example 4. Solving for the interest rate. Solving for an interest rate is a common TVM problem that can be easily addressed with a financial calculator. Let's return to our earlier example, but in this case, we know that we have $1,000 at the present time and that we will need to have a total of $1,125, 4 years from now. Let's also say that the only way we can add to the current value of our savings is through interest income. We will not be able to make any further deposits in addition to our initial $1,000 account balance. What interest rate should we be sure to get on our savings account in order to have a total savings account value of $1,125, 4 years from now? Once again, clear the calculator and then enter 4 for N, minus 1,000 for PV, and 1,125, 51 for FV. Then, press the CPT and IY keys, and you will find that you need to earn an average 3% interest per year in order to grow your savings balance to the desired amount of $1,125. 51. Again, if you end up with an error message, you probably failed to follow the sign convention relating to cash inflow and outflow that we discussed earlier. To correct this, you will need to clear the calculator and re-enter the information correctly. After you believe you are done and have arrived at a final answer, always make sure you give it a quick review. You can ask yourself questions such as, does this make any sense? How does this compare to other answers I have arrived at? Or, is this logical based on everything I know about the scenario? Knowing how to go about such a review will require you to understand the concepts you are attempting to apply and what you are trying to make the calculator do. Further, it is critical to understand the relationships among the different inputs and variables of the problem. If you do not fully understand these relationships, you may end up with an incorrect answer. In the end, it is important to realize that any calculator is simply a tool. It will only do what you direct it to do and has no idea what your objective is or what it is that you really wish to accomplish. Think it through. Determining interest or growth rate here is another example of using a financial calculator to solve a common time value of money problem. Let's use a similar example to the one we used when calculating periods of time to determine an interest or growth rate. You still want to help your child with their first year of college tuition and related expenses. You also still have a starting amount of $15,000, but you have not yet decided on a savings plan to use. Instead, the information you now have is that your child is just under 10 years old and will begin college at age 18. For simplicity's sake, let's say that you have 8.5 years before you will need to meet your total savings target of $25,000. What rate of interest will you need to grow your saved money from $15,000 to $25,000 in this time period, again with no other deposits or withdrawals? Solution: follow the steps shown in Table 7. 7. Step description: enter display 1 clear calculator register CEC002 enter present value as a negative integer 15,000 plus PV equals minus 15,000. 03 enter time periods 8. 5 NN equals 8. 5004 enter future value 25,000 FV equals 25,000. 05 indicate no payments or deposits. PMT equals 006 compute interest rate CPT IY equals 6. 1940 Table 7 calculator steps for determining interest. Rate. The result of this calculation is a necessary interest rate of 6,194%. Using Excel to solve TVM problems. Excel spreadsheets can be excellent tools to use when solving time value of money problems. There are dozens of financial functions available in Excel, but a student who can use a few of these functions can solve almost any TVM problem. Special functions that relate to TVM calculations are as follows: future value FV, 716 present value PV, 717 number of periods NPER, 718 interest rate 7. 19 Excel also includes a function called payment PMT that is used in calculations involving multiple payments or deposits, annuities. These will be covered in time value of money II. Equal multiple payments. Future value, FV. The future value function in Excel is also referred to as FV and can be used to calculate the value of a single lump sum amount carried to any point in the future. The FV function syntax is similar to that of the other 4 basic time value functions and has the following inputs, referred to as arguments, similar to the functions listed above: rate, interest rate 7, 20 N per. Number of periods 721 PMT. Payment 7, 22 PV. Present value 723 lump. Some problems do not involve payments, so the value of PMT in such calculations is 0. Another argument, type, refers to the timing of a payment and carries a default value of the end of the period, which is the most common timing, as opposed to the beginning of a period. This may be ignored in our current example, which means the default value of the end of the period will be used. The spreadsheet in Figure 7.3 shows 2 examples of using the FV function in Excel to calculate the future value of $100 in 5 years at 5% interest. In cell E1, the FV function references the values in cells B1 through B4 for each of the arguments. When a user begins to type a function into a spreadsheet, Excel provides helpful information in the form of on-screen tips showing the argument inputs that are required to complete the function. In our spreadsheet example, as the FV formula is being typed into cell E2, a banner showing the arguments necessary to complete the function appears directly below, hovering over cell E3. Screenshot of FV function within Excel. Cells E1 and E2 show how the FV function appears in the spreadsheet as it is typed in with the required arguments. Cell E4 shows the calculated answer for cell E1 after hitting the Enter key. Once the Enter key is pressed, the hint banner appearing in cell E3 will disappear. The second example of the FV function is in cell E6. The actual numerical values are used in the FV function equation rather than cell references. The method in cell E8 is referred to as hardcoding. Figure 7.3, using the FV function in Excel cells E1 and E2, show how the FV function appears in the spreadsheet as it is typed in with the required arguments. Cell E4 shows the calculated answer for cell E1 after hitting the Enter key. Once the Enter key is pressed, the hint banner hovering over cell E3 will disappear. The second example of the FV function in our example spreadsheet is in cell E6. Here, the actual numerical values are used in the FV function equation rather than cell references. The method in cell E8 is referred to as hard coding. In general, it is preferable to use the cell reference method, as this allows for copying formulas and provides the user with increased flexibility in accounting for changes to input data. This ability to accept cell references in formulas is one of the greatest strengths of Excel as a spreadsheet tool. Download the spreadsheet file containing key Chapter 7 Excel exhibits. Determining future value when other variables are known. You have $2,000 invested in a money market account that is expected to earn 4% annually. What will be the total value in the account in 5 years? Present value, PV equals $2,000. 724. Note, be sure to follow the sign conventions. In this case, the PV should be entered as a negative value. Interest rate, rater I/Y, equals 4%. 725. Note, in Excel, interest and growth rates must be entered as percentages, not as whole integers. So 4% must be entered as 4% or 04, not 4, as you would enter in a financial calculator. Number off periods, n equals 5. 726. Note, it is always assumed that if not specifically stated, the compounding period of any given interest rate is annual or based on years. Future value, FV equals $2,433. 31. 727. Note, the Excel command used to calculate future value is as follows. Equals FV, rate, PMT, PV type. You may simply type the values for the arguments in the above formula. Another option is to use the Excel insert function option. If you decide on this second method, below are several screenshots of dialog boxes you will encounter and will be required to complete. First, go to Formulas in the upper menu bar and select the Insert function option. When you do so, a dialog box will appear that looks like what you see in Figure 7.4. Screenshot that shows dialog box to insert FV function. It shows how to search for a function or select a function that has been used recently. This screenshot shows how to search for FV by typing a brief description of what you want to do and then clicking the Go button, which is next to the search bar, or simply choose FV from the list of the most recently used functions. Since FV is highlighted in the list, an explanation of FV is shown below the list of terms. At the bottom, there is a link for help on this function and an OK and Cancel button. Figure 7.4 dialog box to insert FV function. This dialog box allows you to either search for a function or select a function that has been used recently. In this example, you can search for FV by typing this in the search box and selecting Go, or you can simply choose FV from the list of most recently used functions, as shown here with the highlighted FV option. Once you select FV and click the OK button, a new dialog box will appear for you to enter the necessary details. See Figure 7.5 screenshot of new dialog box for FV function arguments. It shows the data entry screen called Function Arguments and the FV section containing fields for rate, PMT, PV, and type, all numerical fields. Figure 7.5 new dialog box for FV function arguments. Figure 7.6 shows the completed data input for the variables, referred to here as function arguments. Note that cell addresses are used in this example. This allows the spreadsheet to still be useful if you decide to change any of the variables. You may also type values directly into the function arguments dialog box, but if you do this and you have to change any of your inputs later, you will have to re-enter the new information. Using cell addresses is always a preferable method of entering the function argument data. Screenshot of completed dialog box for FV function arguments. In the FV section, all the empty fields are filled with the relevant cell names. Figure 7.6 completed data entry menu for FV function arguments. Additional notes: the PMT argument or variable can be ignored in this instance, or you can enter a placeholder value of 0. This example shows a blank or ignored entry, but either option may be used in problems such as this, where the information is not relevant. The type argument does not apply to this problem. Type refers to the timing of cash flows and is usually used in multiple payment or annuity problems to indicate whether payments or deposits are made at the beginning of periods or at the end. In single lump sum problems, this is not relevant information, and the type argument box is left empty. When you use cell addresses as function argument inputs, the numerical values within the cells are displayed off to the right. This helps you ensure that you are identifying the correct cells in your function. The final answer generated by the function is also displayed for your preliminary review. Once you're satisfied with the result, hit the OK button and the dialog box will disappear, with only the final numerical result appearing in the cell where you have set up the function. The FV of this present value has been calculated as approximately $2,433. $31. Present value, PV. We have covered the idea that present value is the opposite of future value. As an example, in the spreadsheet shown in Figure 7.3, we calculated that the future value of $105 years from now at a 5% interest rate would be $127. $63. By reversing this process, we can safely state that $127. $63 received 5 years from now with a 5% interest, or discount, rate would have a value of just $100 today. Thus, $100 is its present value. In Excel, the PV function is used to determine present value, see Figure 7.7. Screenshot of PV function in Excel. Cells E1 and E2 show how the PV function appears in the spreadsheet as it is typed in with the required arguments. Cell E4 shows the calculated answer for cell E1 after hitting the Enter key. Once the Enter key is pressed, the hint banner appearing in cell E3 will disappear. The second example of the PV function in our example spreadsheet is in cell E6. Here, the actual numerical values are used in the PV function equation rather than cell references. The method in cell E8 is referred to as hardcoding. Figure 7. 7 using the PV function in Excel. The formula in cell E1 uses cell references in a similar fashion to our FV example spreadsheet above. Also similar to our earlier example is the hard-coded formula for this calculation, which is shown in cell E6. In both cases, the answers we arrive at using the PV function are identical. But once again, using cell references is preferred over hard coding if possible. Think it through, determining present value when other variables are known. You have just won a second prize lottery jackpot that will pay a single total lump sum of $50,005 years from now. You are interested in knowing how much value this would have in today's dollars, assuming a 5% interest rate. Future value of V equals 50,000. Interest rate, rater I/Y, equals 5%. Number off periods, n pair n equals 5. Present value, PV, equals 39,176. 31. 728. Notes: if you wish for the present value amount to be positive, the future value you enter here should be a negative value. In Excel, interest and growth rates must be entered as percentages, not as whole integers. So, 5% must be entered as 5% or 0.5, not 5, as you would enter in a financial calculator. It is always assumed that if not specifically stated, the compounding period of any given interest rate is annual or based on years. The Excel command used to calculate present value is as shown here. Equals PV, rate, n per, PMT, FV type. Solution: as with the FV formula covered in the first tab of this workbook, you may simply type the values for the arguments in the above formula. Another option is to again use the insert function option in Excel. Figure 7.8, Figure 7.9, and Figure 7.10 provide several screenshots that demonstrate the steps you'll need to follow if you decide to enter the PV function from the Insert Function menu. First, go to Formulas in the upper menu bar and select Insert Function. When you do so, the Insert Function dialog box will appear, see Figure 7.8. Screenshot that shows dialog box to insert PV function. It shows how to search for a function or select a function that has been used recently. This screenshot shows how to search for PV by typing a brief description of what you want to do and then clicking the Go button, which is next to the search bar. Or simply choose PV from the list of the most recently used functions. Since PV is highlighted in the list, an explanation of PV is shown below the list of terms. At the bottom, there is a link for help on this function and an OK and Cancel button. Figure 7.8 dialog box to insert PV function. As discussed in the FV function example above, this dialog box allows you to either search for a function or select a function that has been used recently. In this example, you can search for PV by typing this into the search box and selecting Go, or you can simply choose PV from the list of the most recently used functions. Once you have highlighted PV, click the OK button, and a new dialog box will appear for you to enter the necessary details. Similar to our FV function example, it will look like Figure 7.9. Screenshot of new dialog box for PV function arguments. It shows the data entry screen called Function Arguments, and the PV section contains fields for rate, NPER, PMT, FV, and type, all numerical fields. Figure 7.9 New dialog box for PV function arguments. Figure 7.10 shows the completed data input for the function arguments. Note that once again, cell addresses are used in this example. This allows the spreadsheet to still be useful if you decide to change any of the variables. As in the FV function example, you may also type values directly in the function arguments dialog box. But if you do this and you have to change any of your input later, you will have to re-enter the new information. Remember that using cell addresses is always a preferable method of entering the function argument data. Screenshot of completed dialog box for PV function arguments. In the PV section, all the empty fields are filled with the relevant cell names. Figure 7.10 completed dialog box for PV function arguments. Again, similar to our FV function example, the function arguments dialog box shows values off to the right of the data entry area, including our final answer. The PMT and type boxes are again not relevant to this single lump sum example, for reasons we covered in the FV example. Review your answer. Once you are satisfied with the result, click the OK button and the dialog box will disappear, with only the final numerical result appearing in the cell where you have set up the function. The PV of this future value has been calculated as approximately $39,176, $31, periods of time. The following discussion will show you how to use Excel to determine the amount of time a given present value will need to grow into a specified future value when the interest or growth rate is known. You want to be able to contribute $25,000 to your child's first year of college tuition and related expenses. You currently have $15,000 in a tuition savings account that is earning 6% interest every year. How long will it take for this account grow into the targeted amount of $25,000, assuming no additional deposits or withdrawals are made? Future value, FV, equals 25,000. Interest rate, rater I/Y, equals 6%. Present value, PV, equals 15,000. Number off periods, NPER, equals 8, 7667. 7.29. Notes: as with our other examples, interest and growth rates must be entered as percentages, not as whole integers. So, 6% must be entered as 6% or 0. 6, not 6, as you would enter in a financial calculator. The present value needs to be entered as a negative value in accordance with the sign convention covered earlier. The Excel command used to calculate the amount of time, or number of periods, is this: equals NPER, rate, PMT, PV, FV type. As with our FV and PV examples, you may simply type the values of the arguments in the above formula. Or, we can again use the Insert function option in Excel. If you do so, you will need to work with the various dialog boxes after you select Insert function. First, go to Formulas in the upper menu bar and select the Insert function option. When you do so, the Insert function dialog box will appear, see Figure 7.11. Screenshot of dialog box to insert NPER function. It shows how to search for a function or select a function that has been used recently. This screenshot shows how to search for the NPER function by typing a brief description of what you want to do and then clicking the Go button, which is next to the search bar. From the Select a Function list, select the NPER function and click the OK button. Figure 7.11 dialog box to insert NPER function. As discussed in our previous examples on FV and PV, this menu allows you to either search for a function or select a function that has been used recently. In this example, you can search for NPER by typing this into the search box and selecting Go, or you can simply choose NPER from the list of most recently used functions. Once you have highlighted NPER, click the OK button and a new dialog box will appear for you to enter the necessary details. As in our previous examples, it will look like Figure 7.12. Screenshot of new dialog box for NPER function arguments. It shows the data entry screen called Function Arguments, and the NPER section contains fields for rate, PMT, PV, FV, and type, all numerical fields. Figure 712, new dialog box for NPER function arguments. Figure 713 shows the completed function arguments dialog box. Note that once again, we are using cell addresses in this example. Screenshot of completed dialog box for NPER function arguments. In the NPER section, all the empty fields are filled with the relevant cell names. Figure 713 completed dialog box for NPER function arguments. As in the previous function examples, values are shown off to the right of the data input area, and our final answer of approximately 877 is displayed at the bottom. Also, once again, the PMT and type boxes are not relevant to this single lump sum example. Review your answer, and once you are satisfied with the result, click the OK button. The dialog box will disappear, with only the final numerical result appearing in the cell where you have set up the function. The amount of time required for the desired growth to occur is calculated as approximately 877 years, interest or growth rate. You can also use Excel to determine the required growth rate when the present value, future value, and total number of required periods are known. Let's discuss a similar example to the one we used to calculate periods of time. You still want to help your child with their first year of college tuition and related expenses, and you still have a starting amount of $15,000, but you have not yet decided which savings plan to use. Instead, the information you now have is that your child is just under 10 years old and will begin college at age 18. For simplicity's sake, let's say that you have 8.5 years until you will need to meet your total savings target of $25,000. What rate of interest will you need to grow your saved money from $15,000 to $25,000 in this time? Again, with no other deposits or withdrawals. Future value, FV equals $25,000. Number off periods, NPER N equals 850. Present value, PV equals 15,000. 730. Note, the present value needs to be entered as a negative value. Interest rate, rate. Note, the Excel command used to calculate interest or growth rate is as follows. Equals rate, NPER, PMT, PV, FV type, guess. As with our other TVM function examples, you may simply type the values for the arguments into the above formula. We also again have the same alternative to use the insert function option in Excel. If you choose this option, you will again see the insert function dialog box after you click the insert function button. First, go to formulas in the upper menu bar and select the insert function option. When you do so, the insert function dialog box will appear. See Figure 714. Screenshot of dialog box to insert rate function. It shows how to search for a function or select a function that has been used recently. This screenshot shows how to search for the rate function by typing a brief description of what you want to do and then clicking the Go button, which is next to the search bar. From the Select a Function list, select the rate function and click the OK button. Figure 714 dialog box to insert rate function. This time, find and highlight rate, and click the OK button once you have done so. The function arguments dialog box will look like Figure 715. Screenshot of new dialog box for rate function arguments. It shows the AUDA entry screen called Function Arguments, and the rate section contains fields for NPER, PMT, PV, FV, and type, all numerical fields. Figure 715 new dialog box for rate function arguments. Once we complete the input, again using cell addresses for the required argument values, we will see what is shown in Figure 716. Screenshot of completed dialog box for rate function arguments. In the rate section, all the empty fields are filled with the relevant cell names. Figure 716 completed dialog box for rate function arguments. As in our other examples, cell values are shown as numerical values off to the right, and our answer of approximately 0.619 or 619% is shown at the bottom of the dialog box. This answer also can be checked from a logic point of view because of the similar example we worked through when calculating periods of time. Our present value and future value are the same as in that example, and our time period is now 85 years, which is just under the result we arrived at 877 years in the periods example. So, if we are now working with a slightly shorter time frame for the savings to grow from $15,000 into $25,000, then we would expect to have a slightly greater growth rate. That is exactly how the answer turns out, as the calculated required interest rate of approximately 19% is just slightly greater than the growth rate of 6% used in the previous example. So based on this, it looks like our answer here passes a simple sanity check review. Learning outcomes by the end of this section, you will be able to explain how the time value of money can impact your personal financial goals. Explain how the time value of money is related to inflation. Explain how the time value of money is related to financial risk. Explain how compounding period frequency affects the time value of money. Single period scenario, let's say you want to buy a new car next year, and the one you have your eye on should be selling for $20,000 a year from now. How much will you need to put away today at 5% interest to have $20,000 a year from now? Essentially, you are trying to determine how much $20,001 a year from now is worth today at 5% interest over the year. To find a present value, we reverse the growth concept and lower or discount the future value back to the current period. The interest rate that we use to determine the present value of a future cash flow is referred to as the discount rate because it is bringing the money back in time in terms of its value. The discount rate refers to the annual rate of reduction on a future value and is the inverse of the growth rate. Once we know this discount rate, we can solve for the present value, PV, the value today of tomorrow's cash flow. By changing the FV equation, we can turn FV equals PV times 1 plus letter 1D45F. Letter 1D45B, 731 into PV equals FV times 1 plus letter 1D45F, letter 1D45B, 732, which is the present value equation. The fraction shown above is referred to as the present value interest factor, PVIF. The PVIF is simply the reciprocal of the FVIF, which makes sense because these factors are doing exactly opposite things. Therefore, the amount you need to deposit today to earn $20,000 in 1 year, n equals 1, at 5% interest is 20,000 times 1, equals 20,000 times 095,238 equals 19,047. 62.7. 33. The multiple period scenario, there will often be situations when you need to determine the present value of a cash flow that is scheduled to occur several years in the future. See Figure 717. We can again use the formula for present value to calculate a value today of future cash flows over multiple time periods. A circular graph shows how when present value compounds, it results in the future value. Conversely, when the future value discounts, the result is the present value. Figure 717 determining future cash flow. An example of this would be if you wanted to buy a savings bond for Charlotte, the daughter of a close friend. The face value of the savings bond you have in mind is $1,000, which is the amount Charlotte would receive in 30 years, the future value. If the government is currently paying 5% per year on savings bonds, how much will it cost you today to buy this savings bond? The $1,000 face value of the bond is the future value, and the number of years n that Charlotte must wait to get this face value is 30 years. The interest rate R is 0% and is the discount rate for the savings bond. Applying the present value equation, we calculate the current price of this savings bond as follows. PV equals $1,000 times 1,00530 equals 1,000 times 230 1,377 equals 231. 38.7. 34. So, it would cost you $231. $38 to purchase this 30-year, 5%, $1,000 face valued bond. What we have done in the above example is reduce, or discount, the future value of the bond to arrive at a value expressed in today's dollars. Effectively, this discounting process is the exact opposite of compounding interest that we covered earlier in our discussion of future value. An important concept to remember is that compounding is the process that takes a present valuation of money to some point in the future, while discounting takes a future value of money and equates it to present dollar value terms. Common applications in which you might use the present value formula include determining how much money you would need to invest in an interest-bearing account today in order to finance a college education for your oldest child, and how much you would need to invest today to meet your retirement plans 30 years from now. TVM, inflation, compounding interest, investing, opportunity costs, and risk the time value of money, TVM, is a critical concept in understanding the value of money relative to the amount of time it is held, saved, or invested. The TVM concept and its specific applications are frequently used by individuals and organizations that might wish to better understand the values of financial assets and to improve investing and saving strategies, whether these are personal or within business environments. As we have discussed, the key element behind the concept of TVM is that a given amount of money is worth more today than that same amount of money will be at any point in the future. Again, this is because money can be saved or invested in interest-bearing accounts or investments that will generate interest income over time, thus resulting in increased savings and dollar values as time passes. Inflation is defined as a general increase in the prices of goods and services and/or a drop in the value of money and its purchasing power. The purchasing power of the consumer dollar is a statistic tracked by the part of the U.S. Bureau of Labor Statistics and is part of the Consumer Price Index, CPI data, that is periodically published by that government agency. In a way, purchasing power can be viewed as a mirror image or exact opposite of inflation or increases in consumer prices, as measured by the CPI. Figure 7.18 demonstrates the decline in the purchasing power of the consumer dollar over the 13-year period from 2007 to 2020. With this in mind, we can work with the TVM formula and use it to help determine the present value of money you have in hand today, as well as how this same amount of money may be valued at any specific point in the future and at any specific rate of interest. A graphical representation of historical purchasing power decline as a result of inflation from the year 2007-2019. Figure 7.18 historical purchasing power decline as a result of inflation, 2007-2020. Data source: Bureau of Labor Statistics. The relationship between TVM and inflation, as we have seen, the future value formula can be very helpful in calculating the value of a sum of cash, or any liquid asset, at some future point in time. One of the important ideas relating to the concept of TVM is that it is preferable to spend money today instead of at some point in the future, all other things being equal, when inflation is positive. However, in very rare instances in our economy when inflation is negative, spending money later is preferable to spending it now. This is because in cases of negative inflation, the purchasing power of a dollar is actually greater in the future, as the costs of goods and services are declining as we move into the future. Most investors would be inclined to take a payment of money today rather than wait 5 years to receive a payment in the same amount. This is because inflation is almost always positive, which means that general prices of goods and services tend to increase over the passage of time. This is a direct function and result of normal economic growth. The crux of the concept of TVM is directly related to maintaining the present value of financial assets, or increasing the value of these financial assets at different points in the future when they may be needed to obtain goods and services. If a consumer's monetary assets grow at a greater rate than inflation over any period of time, then the consumer will realize an increase in their overall purchasing power. Conversely, if inflation exceeds savings or investment growth, then the consumer will lose purchasing power as time goes by under such conditions. The impact of inflation on TVM, the difference between present and future values of money, can be easily seen when considered under the effects of inflation. As we discussed above, inflation is defined as a state of continuously rising prices for goods and services within an economy. In the study of economics, the laws of supply and demand state that increasing the amount of money within an economy, without increasing the amount of goods and services available, will give consumers and businesses more money to spend on those goods and services. When more money is created and made available to the consuming public, the value of each unit of currency will diminish. This will then have the effect of incentivizing consumers to spend their money now or in the very near future, instead of saving cash for later use. Another concept in economics states that this relationship between money supply and monetary value is one of the primary reasons why the Federal Reserve might at times take steps to inject money into a stagnant, lethargic economy. Increasing the money supply will lead to increased economic activity and consumer spending. But it can also have the negative effect of increasing the costs of goods and services, furthering an increase in the rate of inflation. Consumers who decide to save their money now and for the foreseeable future, as opposed to spending it now, are simply making the economic choice to have their cash on hand and available. So, this ends up being a decision that is made despite the risk of potential inflation and perhaps losing purchasing power. When inflationary risk is low, most people will save their money to have it available to spend later. Conversely, in times when inflationary risk is high, people are more likely to spend their money now, before its purchasing power erodes. This idea of inflationary risk is the primary reason why savers and investors who decide to save now in order to have their money available at some point in the future will insist they are paid, through interest or return on investment, for the future value of any savings or financial instrument. Lower interest rates will usually lead to higher inflation. This is because, in a way, interest rates can be viewed as the cost of money. This allows for the idea that interest rates can be further viewed as a tax on holding on to sums of money instead of using it. If an economy is experiencing lower interest rates, this will make money less expensive to hold, thus incentivizing consumers to spend their money more frequently on the goods and services they may require. We have also seen that the more quickly inflation rates rise, the more quickly the general purchasing power of money will be eroded. Rational investors who set money aside for the future will demand higher interest rates to compensate them for such periods of inflation. However, investors who save for future consumption but leave their money uninvested or underinvested in low-interest-bearing accounts will essentially lose value from their financial assets because each of their future dollars will be worth less, carrying less purchasing power when they end up needing it for use. This relationship of saving and planning for the future is one of the most important reasons to understand the concept of the time value of money. Nominal versus real interest rates. One of the main problems of allowing inflation to determine interest rates is that current interest rates are actually nominal interest rates. Nominal rates are stated, not adjusted for the effects of inflation. In order to determine more practical real interest rates, the original nominal rate must be adjusted using an inflation rate, such as those that are calculated and published by the Bureau of Labor Statistics within the Consumer Price Index, CPI. A concept referred to as the Fisher effect, named for economist Irving Fisher, describes the relationship between inflation and the nominal and real interest rates, and is expressed using the following formula. 1 plus I equals 1 plus R times 1 plus H. 735, where I is the nominal interest rate, R is the real interest rate, and H is the expected inflation rate. An example of the Fisher effect would be seen in the case of a bond investor who is expecting a real interest rate of return of 6% on the bond, in an economy that is experiencing an expected inflation rate of 2%. Using the above formula, we have I equals 1 plus R times 1 plus H minus 1 I equals 1 plus 6% times 1 plus 2% minus 1 I equals 8. 12% 736, so the nominal interest rate on the bond amounts to 8. 12%, with a real interest rate of 6% within an economy that is experiencing a 2% inflation rate. This is a logical result because in a scenario of positive inflation, a real rate of return would always be expected to amount to less than the stated or nominal rate. Interest and savings are adversely affected by negative real interest rates. A person who holds money in the form of cash is actually losing future purchasing value when real interest rates are negative. A saver who decides to hold $1,000 in the form of cash for 1 year at a negative real interest rate of -3 65% per year will lose 1,000 times minus 0. 365 or $36. $50 in purchasing power by the end of that year. Ordinarily, interest rates would rise to compensate for negative real rates, but this might not happen if the Federal Reserve takes steps to maintain low interest rates to help stimulate and stabilize the economy. When interest rates are at such low levels, investors are forced out of Treasury and money market investments due to their extremely poor returns. It soon becomes obvious that the time value of money is a critical concept because of its tremendous and direct impact on the daily spending, saving, and investment decisions of the people in our society. It is therefore extremely important that we understand how TVM and government fiscal policy can affect our savings, investments, purchasing behavior, and our overall personal financial health. Compounding interest, as we discussed earlier, compound interest, can be defined as interest that is being earned on interest. In cases of compounding interest, the amount of money that is being accrued on previous amounts of earned interest income will continue to grow with each compounding period. So, for example, if you have $1,000 in a savings account and it is earning interest at a 10% annual rate and is compounded every year for a period of 5 years, the compounding will allow for growth after 1 year to an amount of $1,100. This comprises the original principal of $1,000 plus $100 in interest. In year 2, you would actually be earning interest on the total amount from the previous compounding period, the $1,100 amount. So, to continue with this example, by the end of year 2, you would have earned $1,210, $1,100 plus $110 in interest. If you continue on until the end of year 5, that $1,000 will have grown to approximately $1,610. Now, if we consider that the highest annual inflation rate over the last 20 years has been 3%, then in this scenario, choosing to invest your present money in an account where interest is being compounded leaves you in a much better position than you would be in if you did not invest your money at all. The concept of the time value of money puts this entire idea into context for us, leading to more informed decisions on personal saving and investing. It is important to understand that interest does not always compound annually, as assumed in the examples we have already covered. In some cases, interest can be compounded quarterly, monthly, daily, or even continuously. The general rule to apply is that the more frequent the compounding period, the greater the future value of a savings amount, a bond, or any other financial instrument. This is, of course, assuming that all other variables are constant. The math for this remains the same, but it is important that you be careful with your treatment and usage of rate R and number of periods N in your calculations. For example, $1,000 invested at 6% for a year compounded annually would be worth 1,000 times 1 equals 1,060. But that same $1,000 invested for that same period of time, 1 year, and earning interest at the same annual rate, but compounded monthly would grow to 1,000 times 1,005, 12 equals 1,061. 67, because the interest paid each month is earning interest on interest at a 6% rate. Note that we represent R as the interest paid per period. 0.6 annual interest 12 months in a year equals 0. 5, and N as the number of periods, 12 months in a year. 12 times 1 equals 12, rather than the number of years, which is only 1. Continuing with our example, that same $1,000 in an account with interest compounded quarterly, or 4 times a year, would grow to 1,000 times 1,015, 4 equals 1,061. 36 in 1 year. Note that this final amount ends up being greater than the annually compounded future value of $1,060, and slightly less than the monthly compounded future value of $1. $61.67, which would appear to make logical sense. The total differences in future values among annual, monthly, and quarterly compounding in these examples are insignificant, amounting to less than $1.70 in total. However, when working with larger amounts, higher interest rates, more frequent compounding periods, and longer terms, compounding periods and frequency become far more important and can generate some exceptionally large differences in future values. $10 million at 12% growth for 1 year, and compounded annually amounts to 10,000 times 112 equals 11,200,000, while $10 million on the same terms but compounded quarterly will produce 10,000,000 times 1 equals 11,255,088. 10. Most wealthy and rational investors and savers would be very pleased to earn that additional $55,088. 10 by simply having their funds in an account that features quarterly compounding. In another example, $200 at 60% interest, compounded annually for 6 years, becomes 200 times 1. 6 equals 355. 44, while this same amount compounded quarterly grows to 200 times 1. 24 equals 725. 4. An amount of $1 at 3%, compounded annually for 100 years, will be worth 1 times 1. 100 equals 19. 22. The same dollar at the same interest rate, compounded monthly over the course of a century, will grow to 1 times 1. 25. 200 equals 397. 44. This would all seem to make sense due to the fact that in situations when compounding increases in frequency, interest income is being received during the year as opposed to at the end of the year, and thus grows more rapidly to become a larger and more valuable sum of money. This is important because we know through the concept of TVM that having money now is more useful to us than having that same amount of money at some later point in time. The rule of 72 is a simple and often very useful mathematical shortcut that can help you estimate the impact of any interest or growth rate, and can be used in situations ranging from financial calculations to projections of population growth. The formula for the rule of 72 is expressed as the unknown, the required amount of time to double a value, calculated by taking the number 72 and dividing it by the known interest rate or growth rate. When using this formula, it is important to note that the rate should be expressed as a whole integer, not as a percentage. So, as a result, we have years for an amounto double equals 72 interester growth rate 7. 37. This formula can be extremely practical when working with financial estimates or projections, and for understanding how compound interest can have a dramatic effect on an original amount or monetary balance. Following are just a few examples of how the rule of 72 can help you solve problems very quickly and very easily, often enabling you to solve them in your head, without the need for a calculator or spreadsheet. Let's say you are interested in knowing how long it will take your savings account balance to double. If your account earns an interest rate of 9%, your money will take 9 or 8 years to double. However, if you are earning only 6% on the same investment, your money will take 6 or 12 years to double. Now let's say you have a specific future purchasing need, and you know that you will need to double your money in 5 years. In this case, you would be required to invest it at an interest rate of 7.25 or 4%. Through these sample examples, it is easy to see how relatively small changes in a growth or interest rate can have significant impact on the time required for a balance to double in size. To further illustrate some uses of the rule of 72, let's say we have a scenario in which we know that a country's gross domestic product is growing at 4% a year. By using the rule of 72 formula, we can determine that it will take the economy 4 or 18 years to effectively double. Now, if the economic growth slips to 2%, the economy will double in 2 or 36 years. However, if the rate of growth increases to 11%, the economy will effectively double in 11 or 655 years. By performing such calculations, it becomes obvious that reducing the time it takes to grow an economy, or increasing its rate of growth, could end up being very important to a population, given its current level of technological innovation and development. It is also very easy to use the rule of 72 to express future costs being impacted by inflation or future savings amounts that are earning interest. To apply another example, if the inflation rate in an economy were to increase from 2% to 3%, consumers would lose half of the purchasing power of their money. This is calculated as the value of their money doubling in 72.3, or 24, years as compared to 72.2, or 36 years, quite a substantial difference. Now, let's say that tuition costs at a certain college are increasing at a rate of 7% per year, which happens to be greater than current inflation rates. In this case, tuition costs would end up doubling in 72.7, or about 10.3 years. In an example related to personal finance, we can say that if you happen to have an annual percentage rate of 24% interest on your credit card, and you do not make any payments to reduce your balance, the total amount you owe to the credit card company will double in only 72.24, or 3 years. So, as we have seen, the rule of 72 can clearly demonstrate how a relatively small difference of 1 percentage point in GDP growth, or inflation rates, can have significant effects on any short or long-term economic forecasting models. It is important to understand that the rule of 72 can be applied in any scenario where we have a quantity or an amount that is in the process of growing, or is expected to grow for any period of time into the future. A good non-financial use of the rule of 72 might be to apply it to some population projections. For example, an increase in a country's population growth rate from 2% to 3% could present a serious problem for the planning of facilities and infrastructure in that country. Instead of needing to double overall economic capacity in 72.2 or 36 years, capacity would have to be expanded in only 72.3 or 24 years. It is easy to see how dramatic an effect this would be when we consider that the entire schedule for growth or infrastructure would be reduced by 12 years due to a simple and relatively small 1% increase in population growth. Investing and risk investing is usually a sound financial strategy if you have the money to do so. When investing, however, there are certain risks you should always consider first when applying the concepts of the time value of money. For example, making the decision to take $1,000 and invest it in your favorite company, even if it is expected to provide a 5% return each year, is not a guarantee that you will earn that return or any return at all, for that matter. Instead, as with any investment, you will be accepting the risk of losing some or even all of your money in exchange for the opportunity to beat inflation and increase your future overall wealth. Essentially, it is risk and return that are responsible for the entire idea of the time value of money. Risk and return are the factors that will cause a rational person to believe that a dollar risked should end up earning more than that single dollar. To summarize, the concept of the time value of money and the related TVM formulas are extremely important because they can be used in different circumstances to help investors and savers understand the value of their money today relative to its earning potential in the future. TVM is critical to understanding the effect that inflation has on your money and why saving your money early can help increase the value of your savings dollars by giving them time to grow and outpace the effects of inflation. Opportunity costs. The concept of opportunity cost arises from the idea that there will always be possible options that are sacrificed with every option we decide on, or for every choice that we make. For example, let's consider the decision to go to college after you graduate from high school. This decision, as with just about any other, will involve evaluating opportunity costs. If you choose to go to college, this will result in your sacrificing 4 years of potential earnings that you could have had if you had decided to take a job instead of attending school. Also, in addition to the lost salary, you would be losing out on 4 years of work experience that could have had a positive impact on your resume or your future earnings prospects. Of course, the entire idea behind furthering one's education is that you are hopeful that by choosing to go to college, you will increase the likelihood of earning a greater salary over the course of your lifetime than you would have if you had chosen to join the workforce directly out of high school. So this ends up being a bit of a risk, but one that you have considered. The idea is that you are hoping for a more significant payoff down the road than if you had made the decision not to continue with your studies. When it comes to opportunity costs and the time value of money, It is obvious that there will always be costs associated with every foregone financial opportunity we pass on when we make a different choice. The logical individual can only hope that these choices produce a better end result than if we had made different choices and pursued any of our foregone alternatives. This also applies in situations where we may sit idly by and decide to take no action at all. For example, if you're putting $1,000 in a savings account to save for a house, you may be giving up an opportunity to grow that money in an investment account that would earn a greater rate of return. In another example, being able to calculate the future value of your money will tell you that instead of investing, you probably should be paying down your 24% APR credit card debt that is costing you hundreds of dollars a month, hundreds of dollars more than you might earn from an investment account.